Hello everyone. Hello everyone. We start the class. And do you hear my voice? My voice? Okay. We review second law of thermodynamics for control volume. If you see the equation, the first equation is for rate of entropy inside control mass. Control mass, you know that, you remember that we don't have any inlet or outlet for the system, and the mass of the system is constant. So rate of entropy during process in control mass equal to addition of rate of heat transfer divided by temperature plus rate of entropy generation. We talked about entropy generation. You know that friction, expansion, rupture of something, and finite temperature difference. In control volume, you remember that we talk about it. In control volume, we have inlet and outlet, one of or both of them for the control volume, and the inlet and outlet for the system exist. So rate of entropy generation inside control volume equal to addition of mass flow rate cross entropy for inlets minus mass flow rate of outlet cross entropy plus addition of rate of control volume, rate of heat transfer to control volume divided by T plus rate of entropy generation. So entropy generation is a parameter that we can't compute it directly. So if we delete or remove this term, rate of entropy generation inside control volume is more than addition of mass flow rate cross entropy of inlets minus mass flow rate cross entropy of outlet plus rate of heat transfer divided by temperature. For a steady state process, remember that in a steady state process, all the term differentiate by time is 0. So for a steady state process, rate of every parameter is 0. So rate of entropy inside control volume is 0. So for a steady state process, addition of mass flow rate cross entropy at outlets of the system minus mass flow rate cross entropy of the system at inlets equal to addition of rate of heat transfer divided by T plus rate of entropy generation. So if we only have one inlet and one outlet, this equation converts to mass flow rate cross entropy at outlet minus entropy as inlet equal to addition of rate of heat transfer divided by T plus S generation, entropy generation. Any question? Any question? Okay, we continue. We also study transient process. Transient process is a process that is variation with time occurs in the system. So rate of mass cross entropy inside control volume equal to additions of mass flow rate cross entropy at inlets minus mass flow rate cross entropy at outlets of the system plus addition of rate of heat transfer divided by T plus entropy generation. So if we integral the above equation, is convert to below equation. So between process from initial state 1 to final state 2. So mass at state 2 cross entropy as state 2 minus mass as state 1 cross entropy as state 1 for control volume inside control volume equal to mass of inlets or inlets cross entropy at inlet or inlets minus addition of mass of system at outlets cross entropy as outlet or exit plus integral of rate of heat transfer divided by T dT plus entropy generation between state 1 and 2. Now consider the steady state for single flow process. Heat transfer plus enthalpy at inlet plus kinetic energy at inlet plus potential energy at inlet equal to entropy at outlet plus kinetic energy at outlet plus potential energy plus work. And the second law, entropy at inlet plus entropy generation plus integral of differential of Q divided by T equal to entropy at outlet. You remember that del differential of heat transfer equal to T temperature cross differential of entropy minus T differential of entropy generation equal to differential of S minus specific volume cross differential of P minus temperature cross differential of entropy generation. So if we compute Q from the above equation between inlet and exit, differential of Q equal to differential of integral of differential of H minus control volume specific volume cross differential of P between state I and E, inlet and exit, minus temperature cross differential of entropy generation between inlet and exit equal to enthalpy at exit minus enthalpy at inlet minus specific volume cross differential P between state I and E minus T differential entropy generation between state I and E. So for a steady state process, work is equal to heat transfer plus enthalpy at, for single flow process, enthalpy at inlet minus enthalpy at outlet exit plus difference or variation in kinetic energy plus variation in potential energy. So it's convert to enthalpy at exit minus enthalpy at inlet minus integral between state I, inlet and E, specific volume cross differential pressure minus integral of between state I and E, T differential of entropy generation plus enthalpy at I minus enthalpy at exit E plus variation in potential energy and variation in kinetic energy. So from the above equation, the work can be computed from the above equation. So if we have a steady state process, reversible process, no kinetic energy, no potential energy variation, and also adiabatic process, the last page equation is convert to work equal to minus integral between state I and E, specific volume crossed by differential P. Any question? Cosm is not the same as Bernoulli equation. Bernoulli equation is an equation that we didn't consider to friction, to irreversible process, on all the process are ideal. So if we neglect that process, this equation can be converted to Bernoulli equation. Any other question? Okay, we continue. Consider a steady state process. You can see it in this equation. So we try to solve a problem. Consider steam enters a steam turbine that you can see it in the figure at a pressure of 1 megapascal, a temperature of 300 centigrade, and a velocity of 15 meter per second. The steam leaves the turbine at pressure of 150 kilopascal and a velocity of 200 meter per second. Determine the work per kilogram of steam flowing through the turbine and assuming the process be a reversible and a adiabatic. So you can see its process in the figure between state I at inlet and E at exit. What we have: pressure, temperature, velocity at inlet, pressure, velocity at outlet. What the problem want from us? Work. So you can see it in temperature entropy diagram. So the process is isentropic. Why is process is isentropic? Because the process is irreversible and adiabatic. Irreversible and adiabatic process is isentropic. So entropy is constant between state I and state E. What equations we have? Continuity equation. We have only in one inlet, one outlet. So mass flow rate at exit equal to mass flow rate at inlet. The other equation is energy equation. First law of thermodynamics. Enthalpy at inlet plus kinetic energy at inlet equal to enthalpy at outlet plus kinetic energy at outlet plus work. The second law, because of isentropic process, we only have entropy at inlet equal to entropy at outlet. So from the table with temperature and pressure, we can compute the enthalpy from state I and entropy at state I. At outlet, we only have pressure 0.15 megapascal, but the other quantity we know that process is isentropic. So entropy at exit equal to entropy at inlet. From the inlet condition, we computed the entropy. So at the outlet, we have entropy, but the pressure is known. If we consider the table of thermodynamics, entropy at exit equal to entropy for liquid state plus quality value at exit cross entropy Fg, means entropy of vapor minus entropy of liquid. If we consider to the table, quality can be computed 0.98 to 7. And from this value we can compute the enthalpy at exit. So from the last equation, enthalpy at inlet, entropy, kinetic energy at inlet, enthalpy at exit, kinetic energy at exit, all of them are known. So we can compute the work that equal to 377.5 kilojoule per kilogram. Any question? Okay, we continue for the next example. Consider a compressor have received saturated refrigerant 134A as a vapor at minus 20 centigrade and deliver the vapor at 1 megapascal and 40 centigrade. The compressor considered as adiabatic. Does this process violated the second law? So what we should check? We should check the second law of thermodynamics. Because of a steady state process, the entropy at exit equal to entropy at inlet plus entropy generation. From the table of R134A, we see that entropy at exit because of temperature and pressure equal to 1.7148 kilojoule per kilogram Kelvin, and entropy at inlet during to vapor state at minus 20 centigrade equal to 1.7395 kilojoule per kilogram Kelvin. So entropy as inlet is more than entropy as outlet. So we consider the equation entropy at exit should be more than entropy at inlet. But what we have, entropy at inlet is more than outlet. So this quantity is violated the second law of thermodynamics. Any question? So we continue to solve other example. An air compressor is a take in a flow of ambient air of 100 kilopascal and 290 Kelvin and compress this air to 1000 kilopascal in an reversible adiabatic process. So we want to know the specific work required and the exit air temperature. So the compressor is a control volume. So according to assumption of example, process is adiabatic. So rate of heat transfer to environment is equal to 0. What equation we should use it in this example? The first is continuity. Mass flow rate at inlet and outlet of compressor are equal to each other. The other equation is energy equation. So mass flow rate cross enthalpy at inlet equal to mass flow rate cross enthalpy at exit plus rate of work. The second law of thermodynamics, mass flow rate cross entropy at inlet plus rate of entropy generation equal to mass flow rate cross entropy at exit. And also the process is reversible according to assumption of problem. So entropy generation is 0 for reversible process. So according to isentropic process, we can consider with constant specific heat and K, entropy at exit equal to entropy at inlet. So from the isentropic process, T at exit equal to temperature at inlet cross pressure at exit divided by pressure at inlet power to K minus 1 divided by K. So this value, the temperature is 559.9 Kelvin. So with the computation of temperature, work of compressor equal to enthalpy at inlet minus enthalpy at exit equal to constant specific heat cross temperature at inlet minus temperature at exit. So from the above equation, the work is minus 251 kilojoule per kilogram. But why is it minus? Because we need work. The work should be inter to the system. The compressor should be connected to electricity network. Without it, we can't compress the pressure, compress the air of the inlet. So, any question? Okay, it's not it's not any problem. Abdul Sadat, he can see the lecture of the class. It's recorded and he can see it in the next time, other time. Yes, the grade be modified. All the students that sent to me the answer, send me the project or will send me the project, I increase the number and put grades and increase their grade without any problem. Any other question? Okay, if you don't have any question, we can close the class and continue the lesson tomorrow. Be successful. Bye.